detail we were walking on was the idea of how to measure a distance between points on the plane. And we did it in a particular case, with two just randomly chosen points, whatever. With the idea being, so you can measure the distance between those 2 points. Do you think you can measure the distance between any two others? And let's do it explicitly in a single example. This isn't necessarily in the notes, but here's, how about this? 1, 5, 2, 2, 2. If I were to ask you to measure the distance between these 2 points, well, maybe I'll give you 2 options. You can discuss this question, or I can talk through it. Would people have me keep talking? Cool. Seeing no hands, compute this distance. You can talk to each other as much as you would like. You can even ask me questions if you want. I guess I should have this written down here. Neato. What are people getting the distance to be? Let's follow the algorithm that we got at the end of class last time. So, what did we do last time? We said, well, if you want to measure the distance between these 2 points, let's build a right triangle and use the Pythagorean formula. So build this right triangle, and let's determine the lengths of the sides. And I guess to do that, let's locate this point where that right angle is. What should the x coordinate of that point be? Yeah.
1, 2.
Excellent, both entries. So it should be 1, because it should have the same x value as that, y value 2. So there is the coordinates of that point. So can you determine the height of that triangle? What do you get? 3, because it should be 5 minus 2. How about the base of that triangle? 1. Why 1?
Because it's already at 1, and then you can just go to 2.
Excellent. You need to go from this x value to that x value. You do that in a step of 1. All right. Is that everything we need to use the Pythagorean theorem? Yeah. So the Pythagorean theorem says that the hypotenuse should have length equal to the square root of the sum of the squares of the remaining sides. So square root of, let's use the horizontal one first. 1 squared plus 3 squared. And from there, I guess it's just simplify. What's 1 squared?
1,
3 squared?
9,
1 plus 9?
10.
Does that have any perfect square factors we could use to simplify? No. So square root 10. Nice. That idea seemed pretty okay. Do you think you could now do that with absolutely any pair of points? And if you do, I think you'll wind up getting just like a formula. Where did this 1 come from? It came from the difference between the x values. Where did this 3 come from? It came from the difference between the y values. So as a consequence, I'm going to flip to the next page. We'll get a formula. The distance formula in the plane says the distance between any points x1, y1, and x2, y2 is given by the square root of the difference between the x values plus the difference between, squared, plus the difference between the y values. Yeah.
Does it matter which order the x1 and x2 come? Because I did it with the other way around, I got the same answer.
Awesome. Let's talk about whether or not it matters. So let's focus on maybe even just a single ingredient. So let's imagine that you swapped the order of those. So maybe we'll even be explicit. So on the previous page it was 2 and 1, right? Those were the x values. So let's see, 2 minus 1 squared. The other one would have been 1 minus 2 squared. So let's just try to walk out from the inside out what those two things are. 2 minus 1 is 1 squared. 1 minus 2 is negative 1 squared. Also notice like the things inside the square, just one of them is the additive opposite of the other. Does that negative sign actually matter if you square it?
No.
Yeah, so the order doesn't matter. In fact, if you wanted to be like really picky, the formulas suggested by what we did on the previous page should have like absolute values around them. Because I wanted the distance between the x values, not the difference between them. But with that square there, do the absolute value bars even matter? No. So it's another layer of complexity that you don't need. It doesn't affect the formula. So they shouldn't actually be here. Folks feel pretty nice? All right. So here is a game I would like to play. We have this distance formula. And the distance formula says if you want to measure the distance between 2 points in the plane, then you can do that by measuring the difference between their horizontal and vertical components. Well, we have some examples of points sitting on planes in this classroom, namely the corner points of the classroom. Here's what I would like to happen. I have 4 tape measures, not enough for everyone, but enough for like groups to form. I will distribute them accordingly. 2 and a 4, 2 and a 9. Form up groups. Here's the task I would like you to accomplish. Pick a wall, or ceiling if you like. Determine the distance between opposite corner points of that wall, or ceiling. You will have to stand up and move around to accomplish this goal. Or at least someone who has a tape measure left. So group up around, so people with tape measures, hands up. Find someone with a tape measure, go to them. If you don't want the tape measure, then I guess give it to someone else. Take your pick.
We should go to the back row because it'll be hard to measure exactly.
You want to just go to that corner?
be the eventual goal. The first goal is pick two corners on the same wall. Or like the two ceiling corners.
Wait, I think you're right actually, because it's not gonna be accurate.
Expenses were spared concerning the amount I spent on these tape measures.
So we'll just go to the corner. What are you at? Wait, no, this is. Does it have to be exact? Can you be round or does that have to be exact?
I mean, it can't be exact, it's an actual measurement. So, you will. The degree to which you round is up to you.
It's almost 24. It's just, it's like a 16 for this is not. This is like at least 30.
Limbo.
Sorry. Yep, there we go.
Are we measuring here to here?
Yeah, I want diagonal corners. Yeah, I want the thing that makes you use the distance formula.
Oh, damn, we're gonna have to really duplicate something. Yeah, we do it here.
You can let it.
Oh, yeah. Okay, you have it. Can you see that?
Wait, if you get on the chair, then you should be able to like pull it up higher.
Oh gosh, don't stand on the wheelie chair, please.
Oh. You're about like 4
Plus 4, right? 6 foot.
So,
11 is right at the end.
so 32 feet. That's okay.
Should we just convert?
Yeah, I don't think it's
17 8-inch fronts, tall, so I didn't do math.
What was the first one? 25.
So 300 inches, 300, 787.
Yeah, that's what I was doing, but I got.
Did you convert the inches to feet?
Yeah.
What did you get?
11.
So we just gotta do 11 times, or 11.3 times 17.
Yeah, so 134. Oh, no, I did, because I did 17 times 8 to get 136 and then divided that by.
Oh, just,
That is the feet. Oh. 24 feet, what is it? 17 times 8, about 96 inches, divided by 12 squared. Oh. You could probably round that to like 0.77. Did you get 26? Added those in. Oh, I didn't do the square root. Well, I don't think this is gonna give it exact. If you wanna do this, that would be our answer. As long as if you wanna double check this, just because I've never typed it out. 26.5. Yeah. I guess you could round that to.
That would be. So it's about 300. Would already be.
This is an inches.
Oh, we're trying to. Yeah.
Okay, so it's 27. I would say 27.
So 27.5.
Yeah. Yeah.
Cool. So, as we come back together, so I want to make one observation first. I know some people are wanting to like calculators in the form of a cell phone instead of a handheld calculator, which is fine in the context of class. Is anyone here not a calculator going on through things? Does anyone not have a calculator that they like? Okay. A thing that you have available to you, regardless of whether or not you answer that question with a yes, is the math department will check out calculators on like exam days. If you go up to the 5th floor, if you take the elevator and you turn right, you'll see a sign that says math department office. If you go to the math department office and go in there and ask them to check out, like, loan you a calculator, they'll ask you for your student ID, then they'll give you a calculator, and then they'll give you your ID back when you give them the calculator back. So, if you need a calculator, you have access to it on things like exams. I'll also try to have like one lunar calculator on exam days, but try to remember to bring and remember to bring are two different things. So, all right, let's bring this together. So, I saw people doing some measurements of like horizontal dimensions. So tell me, not a final diagonal dimension, but tell me one of the lengths that you directly measured.
24 feet
24 feet. Which edge was that?
from that corner to that corner.
So along the back wall. Cool. That should be the same as the dimension of the front wall, I hope. You said 24 feet?
Yeah.
People get measurements that were consistent with that, I hope? How confident are you in that measurement? And let me quantify that question. How much precision do you think you have?
Like 90%.
No, I mean like 24 feet is not the exact value, it can't be. Whenever you measure something, it's not going to be exact. Would you say that you are off by up to an inch or up to 6 inches, or if you want to ballpark it, what would you say?
Probably like 2 inches.
Up to 2 inches in error. Okay, that's just something worth keeping in mind. Then I think 24 feet is a reasonable number to call that. That's a reasonable amount of precision. Alright, give me another edge. Another dimension. Yeah.
Ours that we measured was basically the length of this room and then the height of that.
Mhm.
Then we got, for the length, we got 25 and 7/8 inches, and then for the height, roughly around 11 or 11 feet.
11 feet.
25 and 7/8.
Okay, so 25 feet, 7/8 inches?
Yeah.
Okay, there's some error in there, so your two measurements don't necessarily agree, but I don't care. That's fine. Anyone measure the back to front distance? I mean, I saw people doing it, what'd you get?
We got 32 feet going that one and that was 11.
Nice, which agrees with that, so. I think I'm reasonably confident in that. All right, so let's use these numbers. I'm unhappy enough that we're using like non-metric units, but using the not even base 10 artifact that is inches and feet at the same time absolutely makes me really mad. So I'm gonna use the 24 number because that's gonna be easier. I don't wanna convert to a decimal. You should, 25 and 7/8 inches, 25 feet, 7/8 inches should just be converted to 25 point some number of feet. Or just all 2 inches. Because otherwise you're like walking base 10 and base 12 at the same time, and arithmetic is gonna be a nightmare. Anyway, let's do stuff. Let's, you use these numbers to get a diagonal distance. Give me a diagonal distance that you got.
Like
Yeah.
the final answer.
Yeah,
26.5 feet.
cool. Remind me which wall. The back wall, which should be the same as the front wall. This is gonna be easier to draw the picture. So what you got there was what, say it again?
26.5 feet.
Nice. And you already indicated that you had error of up to a few inches, so I think up to the tenths in the feet measurement is probably okay, yeah. How'd you get that?
We did 11 squared plus 24 squared. Well, we had 11.3, but. So we
Okay,
did 11.3 squared plus 24 squared, and then we took the square root of those.
nice. And, oops. I'm even going to bring the units through a route. Whenever the units are all consistent, everything should work out okay, but it's a nice sanity check to see what units you end up with. The end units better be feet. So let's walk this out. So you did the intervening computations. We'll see how much you wrote down. What was 11 squared?
127.69. But it's technically 121.
Yeah, okay, so it was 11.3. So that's what you said it was?
Yeah.
Nice. And then the feet will also get squared. So 127.69 square feet plus, what was the 24 squared?
576.
576, and again, square feet. And I'm going to need to take the square root of that. So, I guess you did, maybe you did it in steps. What do you get when you add those two things together?
703.69.
703.69. And it's going to be square feet, but inside the square root. So that was exact. I guess that's probably still exact. Next one will be an approximation because you're going to take a square root.
26.5.
26.5. And let's talk about why it should be feet. So right now I have that feet being squared. So that looks like a unit of area, but then I'm going to take a square root. Oh yeah, so it'll become just feet. All right, Vito. That roughly describe what people did in general on that? Nice. So you have the distance formula that allows you can walk two measurements to a thought. So if you want to measure a distance that's hard to measure directly, you can use this formula to indirectly measure a thought. I don't know if you do that, there's be some errors that get introduced, but that's life. All right, people feel okay? Nice. So, let's jump down here. So, this next exercise, it uses the distance formula. But whenever there's like squares and square roots, you want to have them cancel. And if you are too sloppy, there's an error that might happen. So let's go through a distance computation. Lines sorted down one at a time. Let's go through them and see if you can identify an error that occurs. So let's suppose I want to compute the distance between those 2 points. -3.5 to 3.2. And let's just go through one line at a time. So in the first step, I just want to use the distance formula and write down what it says. Is that a correct application of the distance formula? Things written down in the right places? There's a square, there's some subtraction, there's some square roots, and there's an addition. Nice. We feel good? All right. In the next step, apparently I have evaluated the things inside the parentheses. That happened correctly? All right, no errors so far. In the next step, allegedly I evaluate some squares. Do you agree? Happened correctly? All right, nice, nice. We're trucking along. In the next step, I say that I am going to distribute the square root. Is that done correctly? No, why not?
They're supposed to be all under one.
Yeah, square root doesn't distribute. Over addition. So here's a caution. Not everything distributes over addition or multiplication. So if you're going to do tricks involving little algebraic manipulations like that, make sure that they're, correct. And let's imagine you went through and did this computation. You get the end result of 9. Other than going through these line by line and trying to identify an error, what's something you could do to check whether 9 is actually correct? Maybe you have access to a calculator. Do you think you could write that expression into most calculators? Yeah, this won't tell you where the error is. But even if it's a homework problem where I say, don't use the calculator, I want to see all your work, you can use your calculator to check anything you want. So let's pull up a machine. So let's not do any simplification. It's whatever you want to find. Is that expression typed in correctly? Sorry, it's very small. Better? All right, let's see what it says. About 6.7, is that the thing we got on the page with the error in it? No, so errors are introduced, and this doesn't tell you where the error is, but it tells you that something suspicious is happening. So, especially if you think that you're liable to make silly little algebra errors like that, use this sort of idea to check your walk. Nice. So there's some stuff about distance formula. Let's talk about a few more things. I think the 2 remaining formulas that I want are the midpoint, and I think the average slope is going to come up later on. Let's talk about midpoints. So if I give you 2 numbers on the number line, the midpoint between those 2 numbers is just the same as the average between those 2 numbers. And you know what that is. That's you add them up and divide by 2. And let's just see if that works out correctly. Use this formula, compute the midpoint between 4 and 10. Tell me what you get. I hear a 7. I'll wait for a second. Do I hear a second? Excellent. Do I hear a differing answer? Nice. Do I hear a call to do the walk myself? Cool. 7. And let's just see if that looks reasonable. There's a number line, there's 4, there's 10. 7 seem like it's roughly halfway between those? Yeah, so 4, 5, 6, 7, 8, 9, 10. Yeah, that seems about right. I can't draw things to a consistent scale, so it looks a little lopsided, but I think a correct scale would work out right. Similarly, the midpoint between 2 points in the plane is given as follows. Take the midpoint between their x coordinates, then take the midpoint between their y coordinates. Let's write that down. So if you want to compute the midpoint between 2 points in the plane, compute the midpoint between their x values, then compute the midpoint between their y values, and just draw on that point. There should still be a point in the plane. So let's do exactly this for an example. Let's find the midpoint between -1, 3 and 3, 1. Yeah, there's space right here. -1, 3, -3. All right, so, and I'll make the same sort of call as I make sometimes. People want me to do any of the walk myself right now? Should I do it with the computation? Cool, then I will pause for a moment. And you will tell me what the midpoint seems to be according to the formula. Yeah, let's give it a second pause. And maybe it's worth having the formula up. Yeah,
So I got a midpoint of -2, 2.
-2, 2, that agree? Cool. Other people agree? Anyone disagree? Cool. Should I do the computation? Cool. So, I hear a result of -2, 2, and let's just draw a picture to see if it looks reasonable. All right, so let's draw these, -1, 3. So it's -1 in the x direction, 1, 2, 3 in the vertical direction. -3, 1, 3 to the left, 1 up, -2, 2. That seem like it's halfway between those 2 points? Great, yeah. I think the formula seems sensible. So you can compute midpoints between any 2 points. So, with those things out of the way, this allows us to do algebra, to do geometry on the plane. You can measure distances, you can find midpoints, you can compute slopes, though we haven't written down that formula yet. And why is this important? There's a connection between studying functions and thinking about graphs, thinking about things in the plane, and that translation is the graph of a thing. So if I give you an equation, you can visualize solutions to this equation by thinking about them as a graph. So let's write that down. If I give you an equation like 2x minus y equals 6, what does the graph of that equation mean? And I don't know, like, a lot of this I think of as being a review of things you already know. If I ask you what the graph of this means, how many people already have an idea? What should it mean? Yeah.
Just had to find this slope formula, put it into slope formula.
Oh, sure. There are some related ideas. Like this, everything there looks like it's linear.
Okay.
So you certainly could. Here are related ideas. There'll be like a slope that you could find and maybe an intercept for this particular thing. But, and those are like properties of it, but I want what does it mean? What does it mean? And like, I think you know the answer to this in some sense, because like you have a picture in your head, right? Like, you graph this, it'll be a line. But why is it a line? What does that line tell you? Cool, I'm gonna write a thing down, and then like, it will mean exactly what it has to mean. So if you want to talk about the graph of any equation, that just means all points x comma y, right? If I give you a pair of numbers, that's a point in the plane, which satisfy So what is a graph? If I give you an equation, the graph of that equation is just all points where that equation is satisfied. And in this case, you can draw a picture of this because you know it's going to wind up being a line. But you can talk about graphs of more complicated things. And we'll talk about why it's a line in coming days, things like a lecture next week on the topic of linear functions. And then we'll graph those. But for now, let's focus on this. This gives you a condition. The graph is just all points which satisfy an equation. So there's an easy way to answer a yes-no question of, is this point on the graph? You just need to know if it satisfies this equation. So here's a point, 2, 6. Let's just ask a yes-no question. Is it on the graph? I already hear a no. Why?
Because if you were to put in this little formula and plug in the x and the y, it doesn't end up.
Yeah, so let's plug in color code. X equals 2, because there's the x coordinate, and y equals 6, because 6 is the y coordinate. Do the orange and the pink actually look different over projector?
A little.
I'll try to do better than just a little. Let's switch to green then. There, y equals 6 will now be in green. To the equation, let's see what happens. So we'll get 2 times x minus y, which is 6. And you want to know, is that equal to 6? And well, is 2 times 2 minus 6 equal to 6? No, I guess it's equal to -2, I think. But I don't care that it is equal to -2, I just care that it's not equal to 6. And all right, so it's easy to check if a point is on a graph by seeing if it satisfies the equation. Well, easy is the wrong word. Sometimes it's really hard to evaluate things in an equation, but if it's easy to evaluate an equation, then it's easy to check. Let's check the next one. 5, 4 is the next point. Is that on the graph of this equation? I see some people who seem confident. I see more people who seem confident, good. Anyone want me to talk through a thing? Cool, we'll talk through it. So, well, maybe I'll let you all talk through it. So I saw some heads nodding, so that indicates that you think the answer is yes, right? Yeah.
So if you, when you plug it in, you have 2 times 5 and minus 4.
And I would like to know, is that equal to 6? Is it? Great. So, what can you conclude?
0.54 is on the line.
The graph will wind up being a line, but I don't want to drop that one yet. Nice. So, that gives us some things. 5, 4 is definitely on this graph. 1, 2, 3, 4, 5. So I guess that tells me that like a point up here at 5, 4 is on the graph where I'm using this coordinate grid right there that doesn't quite stretch very enough. If you can simplify an equation enough to, you can like do some solving, then I think you can graph lots of points. So let's ask this question. If I fix x equal to 0, do you think I could figure out what choice of y satisfies this equation? I bet. And maybe I'll do the walk. So let's plug in x equals 0 and see what we get. So that would be 2 times 0 minus y equals 6. That look like you can solve it for y? Yeah, so what is that y value? I want it to be -6, right? 2 times 0 is 0, move the negative to the other side. So 0, -6 is on the graph. x equals 0, 1, 2, 3, 4, 5, 6. That point is on this graph. So, what you see remaining is like 3 more yes/no questions. No, 3 more solve for the y value that makes it be on the graph. So I think I will break this up accordingly. When x equals 2, what y value do you get? When x equals 4, what y value do you get? And then we'll do the last one together. So as you go through the walk and you come to a conclusion on the particular problem I've assigned, compare with those around you. That'll also tell me how people are feeling. I guess if you are in a position where there are fewer people around you, that makes things harder. All right, so I think I'm hearing confidence. When x equals 2, what y value do you get? Negative 2. So, negative 2 should be on the graph. Let's draw that point. X equals 2, y equals negative 2. X equals 4.
Before 2, I guess?
I hear a call for x equals 4, 2, y equals 2. Does that agree? I didn't do the walk, so I don't know. Nice. And I assert that when x equals negative 1, I think I get a y value of negative 8. People buy it? All right, you even agree. That makes me more confident because I didn't actually do any of the walk, I just intuited. So, in order to get an idea of the graph, do you think you could do this with like more x values than that? Yeah. And in fact, when you ask a computer to graph a thing, that's exactly what it does. A computer is going to do like 1,000 computations and then plot a bunch of points by doing this sort of thing if you ask it to graph an equation. But after graphing 4 points, I think we can like connect the dots. Well, how would you describe the resulting object? Line. And you all knew that. You were telling me it's a line repeatedly for the past several minutes. In fact, let's even drop a word like slope. What would you say the slope of this line seems to be? 2, I think. And we'll talk about slope in detail in the coming days. So whenever you have an equation, you can think about its graph. And that lets you visualize solutions to solutions to that equation. This linear equation, its graph winds up being a straight line. I think in the interest of not falling yet further behind, let's blow by this. This next example is just another like, give me some points on a graph and then we'll draw a picture. If I even just like draw that, how many people have an idea what the graph will vaguely look like? Yeah, what should the graph look like? Yeah, like a bowl-shaped thing. The technical word being parabola, but bowl-shaped thing. And if you start plugging in some points, you'll see exactly that structure I'm watching. So I'll encourage you to do that like, on your own time. So, a few more words to introduce. Let's talk about x-intercepts and let's talk about y-intercepts. So, there are particular points that are often of interest on a graph, and I'll just tell you what they mean. The x-intercept of a graph is all of the points where the graph hits the x-axis. That seem like a reasonable thing to call x-intercepts? Hope so. All points where graph hits the x-axis. Similarly, the y-intercepts of a graph are all of the points where the graph hits the y-axis. And let's maybe even say what that means. If a point is on the x-axis, then what can you tell me about the coordinate values of that point?
The y value is 0.
Y value is 0. Or an x-intercept, the y value is 0. And right, that makes sense, right? For this particular picture drawn here, there are the two x-intercepts, they have y value 0. So let's write that down here. So it's all points x, y on the graph with y equals 0. Similarly, the y-intercepts are given by all points x, y on the graph with x equals 0. So to find x-intercepts, it looks like y equals 0. To find y-intercepts, x equals 0. By eyeballing this, do you think you could, about where do the x-intercepts of this thing seem to be?
-2 and +2.
The x-intercepts seem to be at about, and I'm going to be a slight pedant here, not at -2, at -2 comma 0, right? The x-intercept is a point, not a number.
Oh.
So, and that's like a really easy oversight to make because it's, oh yeah, no, I do want both of them, but I want the 0 there too. Cool. And those are approximate, so I've drawn the like little squiggle equal symbol because like they're clearly not exact in those values. I think. Yeah. What about the y-intercepts? Where approximately are they? Yeah.
0, 1/2, 3, 0 there.
Okay. You said 1.5, right?
Oh yeah, 1.5, sorry.
Yeah.
I think I said 1.5. Just 1, yeah.
Cool. So 1.5, 3 halves, 1.5, tomato, potato. Cool. Folks feeling good so far? Let's talk about finding these algebraically. We have an equation for this graph, allegedly. Assuming that I've written things down correctly, let's try to use the equation to find these intercepts as well. So oh god damn it, I am absolutely garbage at managing time this semester, it seems. I'm about at time. So let's try to summarize the idea. If I were to ask you just with that equation how you would find the x-intercepts, what would you do? Yeah.
Plug in 0 for the y.
Plug in 0 for the y value, and do you think you could solve that for x if you do that? Yeah. In this case, you can. Equations are sometimes really hard to solve, but I think this one will be easy if you plug in x equals 0 to solve. So, you can do that. Oh yeah, I need those back. You don't get to keep my tape measures. Yeah, so the other two tape measures, I guess as long as they don't leave the room, I'm fine. But maybe bring them up.